this does not seem to do the trick. Maybe I should try this. Or this! We all love a good Wi-Fi connection, meaning a bad one is something everyone hates. And when that happens, there is usually not much you can do about it when it comes to your router, because it is packed with highly engineered electronics. But one thing you sometimes can change is the antenna. And trust me, there are tons of different antennas out there, different shapes, different sizes, all claiming to improve your wireless connection. And I'm curious myself, not only about how these antennas actually work, but also which one performs the best and how easy it is to make my own. Because let's face it, I tried diving into Wi-Fi antenna design before in previous videos, and so far I failed terribly. So let's not waste any more time and let's get started! This video is sponsored by Mouser Electronics, who not only provided all the antennas and testing devices seen in this video, but they are also giving out a free guide to antennas in the real world. So click the link below to check that out. And while you're already at the Mouser website, feel free to browse through their huge electronics component selection to find the components for your next project. Now to get started, I unpacked all the different antennas I got for this video. And once I was done with that, I started taking them apart one by one in order to find out what they're hiding inside. And all I could find were basically different shaped conductors, sometimes in a helical shape, sometimes straight, sometimes with a metal tube attached. The designs were truly interesting to discover. But they all have one thing in common: their job of converting the high frequency alternating signal from our radio source, which can be your router or microcontroller, into a propagating electromagnetic wave. This wave then travels through space and ultimately reaches a receiver antenna, where the reverse then happens and thus we can send over data. Sounds pretty straightforward, but then why do all these antennas look different if they all do the same thing? Well, it has to do with resonance, because our electromagnetic wave is oscillating at a certain frequency. With Wi-Fi it is around 2.4 GHz. But to better explain resonance, let me use these tuning forks here. If I strike this one, then we can hear a tone, which according to the fork should be 440 Hz. To prove that, let me quickly attach a piezoelectric disc to the fork, which can pick up mechanical vibrations, and let's hook that up to the oscilloscope. After striking the fork again, we can really see a wave with a frequency of around 440 Hz. Nice! Now if I attach this piezo disc to other forks and strike the 440 Hz one next to them, then they all seem to care very little and vibrate in pretty much no way whatsoever. The reason is that they all come with different resonance frequencies. But if we use a fork with the exact same frequency, then it magically vibrates as well. And this is the kind of resonance behavior we want from our antenna pair as well, so that we can transmit and receive data. But unlike a tuning fork, which is a purely mechanical resonator, an antenna is an electrical resonator. So the first important property to get an antenna into resonance is its conductor length. You see, for our 2.4 GHz Wi-Fi signal, its wavelength is about 12.5 cm. Simplified speaking, this wave travels in our antenna conductor, and the perfect size to reach a resonance point is at exactly half the wavelength, so around 6.25 cm. Here's an animation from Wikipedia that shows this phenomenon pretty well. And truth be told, we could spend hours here talking about antenna theory. So let's not do that, and instead let's do an experiment with the, I would say, classical looking antennas I got here. Now I want to find out which one can establish the best Wi-Fi connection. And for that, we can make our life easy and grab ourselves two ESP32 microcontroller boards. These come with Wi-Fi and a UFL connector, meaning I can hook up an SMA adapter and thus connect all my antennas easily. So what I did was using a bit of code to turn the first ESP32 into an access point transmitter and the second one into a receiver that connects to the access point and measures the RSSI, aka Received Signal Strength Indicator. This value looks something like this, and the bigger this value gets, the better the connection, and thus the better the antenna. But before getting to that, I firstly wanted to find out how to best position the antennas to one another. And it was honestly no surprise to find out that when positioning both antennas vertical to one another, we get the best results. The reason for that is their radiation pattern, which for such simple straight antennas is kind of like a donut shape, with little radiation on top and bottom and most to their sides. But anyway, with these basics out of the way, I chose a fixed spot for my access point antenna and used a vise and clamp for my receiver antenna. I did that so that I could switch between all the antennas on the receiver side, while keeping the same position and distance to the access point. And after measuring the RSSI for all my antennas, the results were pretty clear, but I wanted to be 100% sure and thus repeated this exact same test with the access point in another room. Here are the final results, and I think it should be pretty easy to spot that there is a clear gap here that basically divides my antennas into two groups. So let's firstly have a look at the better performing group, whose conductor length is around half the wavelength of our Wi-Fi signal, like I mentioned it before. These types of antennas are called dipole antenna. And then we of course got the other group, whose conductor length is a lot shorter. These are called monopole antennas, and their conductor length is only a quarter of our wavelength, so 3.125 centimeter. And in order to reach a resonance point, they simply use the attached ground plane as the missing conductor length. So my monopole antennas were using the ESP32 shielding and my metal vise here as part of the antenna, which is pretty wild, and only this way they achieved such good results. And did you notice that my biggest antenna is also a monopole and did not perform better than my dipoles? Meaning no, bigger is not always better. But anyway, with this experiment out of the way and new knowledge in my head, I wanted to do a DIY attempt, and it seems like a monopole was the easiest to do. So I simply removed the insulation from a solid core wire, cut it to around 3.2 cm and soldered it to an SMA connector. And I actually included this DIY antenna in my experiment from before, and believe it or not, but it performed pretty much as good as the other monopoles. But as you can see, when removing it from the metal vise, aka scaling down its ground plane, then its performance does really go down, meaning a good ground plane is always important for such monopoles. And that brings us to the last plot twist in this video, because while my DIY antenna was cut nicely to the resonance length, the other commercial antennas are not really close, but they also work fine. So what is going on? You see, even if it is just a piece of wire, it always comes with some tiny inductance and capacitance, which do matter though at a high frequency like 2.4 GHz. At resonance frequency, these have to cancel each other out, so that no power gets wasted through them. And that is the point you add things like a helical structure or a metal tube to fine-tune these values. So while length is definitely an important guideline, you also have to keep the inductance and capacitance in mind. And to make things even more complicated, RF systems are usually tuned to a 50 ohm impedance. That means your antenna also needs to match this 50 ohm, otherwise power gets reflected and thus your antenna is not performing great. But here's where we can use a helper tool, a so-called VNA, aka Vector Network Analyzer. After calibrating it and hooking up a commercial dipole antenna, we can see that it performs pretty great at 2.4 GHz with close to 50 ohm. However, if I hook up my DIY monopole, then we can see that it performs pretty terrible and only by attaching a ground plane, we can somehow reach some okay values. And this is only the tip of the iceberg, because we have not yet covered things like return losses, gain of antennas, efficiency of antennas, PCB antennas, chip antennas, or the big directional Yagi antennas that can alter their radiation pattern by using parasitic parts. Yeah, antennas are kind of like an art form, and I'm really starting to like them, so be prepared for a follow-up video about this topic. But for now we can say that if you want an easy and reliable Wi-Fi antenna, then do yourself a favor and get yourself a dipole one. With that being said, I hope you enjoyed this video and learned something new. If so, don't forget to like, share, subscribe and hit the notification bell. Stay creative and I will see you next time!